In this video, I want to talk about some of the properties of integral domains. Let's start by reminding ourselves what an integral domain is. An integral domain is a commutative ring with unity that has the cancellation property. In other words, if A is not equal to 0 and AB is equal to AC, then B is equal to C. Equivalently, we could define it as a commutative ring with unity that has no zero divisors. In other words, if AB is equal to 0, then either A is equal to 0 or B is equal to 0. Let's look at defining multiples in an integral domain. Let's suppose I have some element A that I want to add repeatedly, A plus A plus A plus A, etc. And I want to add it n times. I'm going to denote this as n times A. We also will define 0 times A to be equal to 0, and negative n times A to be equal to negative n times A for all positive integers n. So this tells me that if I have m times A plus n times A, it's the same thing as m plus n times A, and m times n times A, it's the same thing as mn times A. So this is the additive version for the law of exponents. And so this would be how multiples work, corresponding to how exponents work when we multiply. Let's look at order. So remember that if A is a ring, then A with just addition is also a group. So let's consider an element A of my ring capital A. I want to define the order. The order of this element is going to be the smallest positive integer n, such that n times A is equal to 0. And if this integer n doesn't exist, then we say A has order infinity. So to emphasize that we are using addition here, we often call this the additive order of A. And I want to define what's known as the characteristic of a ring. Let's let A be a ring with unity. If my unity element 1 has an additive order of n, then we say A is characteristic n. And if the additive order is infinity, then we say it has characteristic 0. The first thing I want to show, all non-zero elements in an integral domain have the same additive order. So that is, for every non-zero element A, it has the same additive order as 1. So let's consider n times A, where n is the order of my unity element 1. Well, this means A, A, etc. n times, which is the same thing as 1 times A, plus 1 times A, plus 1 times A, etc. n times. I can factor out the A to get 1 plus 1 plus 1 n times A. Well, this is n times 1 times A. So this tells us that n times A is equal to 0 if and only if n times 1 is equal to 0. And this is because we know A is not equal to 0. If n times A is equal to 0, then I have 0 is equal to n times 1 times A. And in an integral domain, if I have a product equal to 0, one of the elements has to be equal to 0. So it must be n times 1. So therefore, all elements have the same additive order. In fact, in an integral domain with non-zero characteristic, the characteristic is a prime number. Let's suppose the characteristic is a composite number, m times n. Then, m times 1, n times 1. Well, m times 1 is 1 plus 1 plus 1, etc. m times n times 1, 1 plus 1 plus 1, etc. n times. Using my distributive property, I get this is 1 plus 1 plus 1, etc. Mn times, which would be the same thing as Mn times 1, which must be equal to 0. Since this is an integral domain, I have a product here equal to 0. So m times 1 is equal to 0, or n times 1 is equal to 0. But that's impossible since mn was chosen to be the least positive integer. So therefore, it can't be equal to a product, and it has to be a prime number, mn. The last thing, which I will not prove here, in any integral domain of characteristic p, where p is a prime number, we actually have that a plus b to the p power is equal to a to the p plus b to the p. Like I said, I will not prove this, but it becomes pretty clear when you look at the binomial expansion of a plus b to the p power. All of the coefficients besides the first one, the a to the p, and the b to the p term, all of the rest of the coefficients are going to be some multiple of p. And therefore, they're all going to cancel out and go to 0 in this characteristic p integral domain.